AQA GCSE Combined Science, June 19, Paper 1, Question 6, the last question. Right, so this is radioactivity. So what happens to the mass number of this stuff, lanthanum-140, when it emits gamma radiation? So this could catch you out because you study what happens when alpha decay happens, 2 protons and 2 neutrons leave. When beta decay happens, when a neutron changes into a proton and an electron's emitted. But gamma radiation's skimmed over because nothing happens. It's a way of getting rid of extra energy from the nucleus. So basically everything's going to stay the same. So it stays the same. And then they've asked, why is it difficult to detect gamma? Now, this is a roundabout way of checking whether you know which ones are more ionising. Because if you get a Geiger counter, and if you remember, a Geiger counter is something that's used to detect radiation. There you go, I've just drawn you a Geiger counter. This is the Geiger-Müller tube. If you have your sample that's giving off radiation, it has to go into this tube and it has to do something. It has to ionise it. It has to ionise a wire inside that tube and then it detects the radiation. So gamma is difficult to detect because if you remember, alpha is the most ionising, beta in the middle, gamma is the least ionising. So when it goes into the tube, quite often it doesn't ionise it. It just goes through the tube and out the other side. So it is not very ionising, which I think was a rather unpleasant question, to be honest. Right, next part of the question. Oh, for this part of the question, it wants to know, it says that activity is the rate at which a radioactive source decays. Now that's going to be important later on, actually. A teacher measured the count rate, which is the number of clicks that happen in the Geiger-Müller tube, and it says why the count rate was less than the activity. So if I go back to my little drawing, which I'm quite proud of, and this is my little lump of metal of lanthanum, and that's emitting radiation in all directions. Now if you could count each of these things that are emitted every second, that would be the activity. The count rate is what the Geiger-Müller tube detects. Now look at this one. This one's going up here. That's not going to go into our Geiger-Müller tube. This one's not going to. This one's not going to. Only this one is going to go in the Geiger-Müller tube. So not all of the decays result in the radiation going into the detector. And that's basically what the answer is to this one. So I'm going to describe that picture in words. So the radiation goes in all directions. So only some, or a proportion, go into detector. So it doesn't record as much. Okay, next one. This is the sort of thing we did in class. In fact, we did do this in class. We had lanthanum, I had some lead, and I had this Geiger-Müller tube that was detecting it, and I showed you that it clicked like crazy when the gamma rays went into it. But I didn't stand close to it. And that's because I do not want to be exposed to radioactivity, because it increases the risk of a mutation in a cell leading to cancer. So I wanted to step away to reduce how much I receive, or reduce the dose, or reduce irradiation is another way of phrasing it, because the radiation can cause cancer. So 2 marks. I stood away to reduce my exposure. Why? Because radiation can cause or causes cancer. And that's what that one was about. Let's go to the next question. So this is 6.5, and I think this was a little unfair to put on a GCSE paper. It's talking about things being inversely proportional or not. And inversely proportional means that as one number goes up, the other number goes down by the same proportion. So for example, if something doubles, like in this case, if the thickness of the lead doubled, the count rate would go down by a factor of 2, or would halve. Similarly, if the thickness tripled, the count rate would go down by a factor of 3. So that's one way of approaching this question. You could say, look, as the thickness of the lead doubled, the count rate should have halved. But it doesn't. 110 should have become 55 if it was inversely proportional. Similarly here, as this tripled to 1.5, this should have gone down by divide by 3. It should have been, well, not 33, a number a bit bigger than 33. So it's not inversely proportional. There's another trick to this though, and this is what the mark scheme wanted. So I'll show you this here. If something is inversely proportional, it means A is proportional to 1 divided by the number. That means that if you multiply the two numbers together, you should get a constant, a number that stays the same. That means if you multiply this number by this number, if I do that, I get 55. If I multiply this number by this number, if it is inversely proportional, I should get 55 again. 1 times 60 is 60, not 55, not inversely proportional. And you could have used either of those approaches, talking about this one doubling, this one should halve, or this idea of multiplying the rows together and getting the same number each time. Okay, right. Next, and sort of the end of the paper now really. So this is going to be a question showing that the number of cerium-148 atoms, and that's a very big number, is going down over time. So one thing that's a bit of a trick to this is that earlier on in the question it said, which I've lost now, here we go, activity is the rate at which a radioactive source decays. Rate is how quickly something changes each second. That means the steepness of this line is the activity. The gradient is the activity, and that's going to be useful in a minute. So let's see what this question is all about. So turning over to the back page, upside down, sorry about that. Here we go. Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared to when it was 350 seconds old. So, first of all, let's find the half-life first of all. So the half-life of this, if I go to the graph, I've already scribbled a line on this, ignore that for a second. We start at 5. How long does it take for that to fall in half? Read along and down. 50 seconds. So the half-life is 50 seconds. So half-life equals 50 seconds. Now it says, what's the ratio of the number of atoms in the sample when it was 100 compared to 350? So at 100 seconds old, there'll be a certain number of atoms there. Then as time goes on, there gets less and less and less. And every half-life that passes, the amount you've got halves. So how many half-lives is that? So 350 minus 100 equals 250 seconds. That's the time difference that they're asking about in the question. And that's going to equate to 5 half-lives. 5 50s is 250. So 5 half-lives pass. What we need to work out now is what's going to happen. So you started off with an original amount at 100 seconds. After 1 half-life, you have half of what you originally had. 2 half-lives, a quarter. 3 half-lives, an eighth. 4 half-lives, a 16th of what you originally had. And 5 half-lives, a 32nd of what you originally had. So the ratio is 1 to 32. There's 1/32th of what you originally had. So 1 over 32. And then finally, and this is what I was speaking about a second ago, about rate being the gradient of that line. Sorry, activity being the gradient of the line. So what was the activity when the sample was 20 seconds old? So you go back to your graph. You go to 20 seconds, that's this point here. And, well, actually, I would think very few people would work out from the question that activity was the gradient of that line. But they've asked you for activity. This does not say activity. This does not say activity. It's a curve, and one of the things that you need to know for GCSE science is finding tangents. And whenever you see a curve, you can find a tangent. So the gradient is the tangent of this line. So you take a ruler. I'm cheating, I don't have a ruler. I'm going to use a bit of paper. And you draw a straight line that just kisses at that point. And then you work out the steepness of this line. So that's the change in the number of cerium atoms. So it's this length here divided by this time here. And when we do that, upside down, right way up, the gradient equals 5.3. And that is your 3 marks. In fact, it's 5.3 times 10 to the 21. But you got full marks for just getting the 5.3. And that is the end of the paper. Thank you.